doing orbital velocity and it's circular, right? When it was a circular orbital velocity, we said, right, that we could use gm over r, okay? When it's a situation where you have an ellipse, right, and you've got an elliptical orbital velocity, I should probably write elliptical, but I'm just going to write ellipse orbital velocity. That's when you do the conservation of angular momentum. So RA VA equals RB VB. Okay, that's that conservation of angular momentum. But what we're going to talk about now is we're going to talk about, I'm going to highlight these just to clarify. We're going to talk about what's the velocity that allows you to escape Earth's gravity. That means it's just enough velocity to get you out of Earth's gravity. All right, so I want you to consider two positions, right? You have the position you're starting at. This is V, that's going to be V orbital, okay? And it's R, its radius is R orbital, so R orbital, and then V orbital. And then when you get out of Earth's gravity, okay, we're just going to get out of Earth's gravity. So when we just get out of Earth's gravity, so R is going to be, R is not going to be that, but our U is good. Our gravitational energy is going to be 0. So we're going to escape Earth's gravity. We're also just going to get there. So we'll get there and we'll stop, which means at that point where we stop, our kinetic final is 0. This is when you've escaped. Okay, so we're basically doing a conservation of energy from orbit to escape. We're doing a conservation of energy from orbit to escape. All right, so what are we doing? We're doing the gravitational energy in the orbit plus the kinetic energy in the orbit is equal to the gravitational energy escape plus the kinetic energy escape, all right? And the gravitational energy in the orbit is just going to be negative g times the mass of the planet times the mass of the spaceship divided by r, plus the kinetic energy is going to be 1/2 times the mass of the rocket times v escape squared. All right, so gravitational energy plus kinetic energy, that's of your orbit, right? And we're going to try to escape. But guess what? The other two are 0 because when you escape, those are both 0.
Even the kinetic?
Yeah, the kinetic 0 because you just get there.
Oh.
You just get there. Okay, it's just enough to get you out.
Oh, yeah. All right.
And so the good news then is I can write it this way. mv escape squared is equal to gmm over r, okay? And then here's the good news. The m's cancel, okay? V escape squared is going to be g 2gm, put the 2 up there, divided by r. So V escape is going to be the square root of 2 times g, which is a constant, right? Times the mass of the planet or the sun or whatever you're escaping, right? This is the big mass, right? Divided by how far you are away from the center of mass of the planet when you escape. So this is my formula. Instead of the square root of gm over r, it's the square root of 2gm over r. And I think it was Colin. I remember a student, and I wanted a mnemonic device, and he said, Ms. Esposito, the escape velocity is the route to going more places rapidly. The route to going more places rapidly. All right?
Wow, that's a clever
Inspiration.
That man
Yeah.
could have done several.
Okay, or you could do 1/2 mv squared is equal to gmm over r. That also works, right? So V escape is the route to going more places rapidly. That helps you. This gives you some escape velocities, right? 11,200 meters per second for Earth. 2,000, the gravitational field on Moon is less, so 2,380. Mars is 5,030. Jupiter, 59,500. And then Sun, 617,700 meters per second. That's how fast you have to be going to escape the gravitational field of the sun. Yes, Alex, and then Sean. No, that's just fun facts.
I'll remember that.
Okay, yes.
Is this stuff gonna be on the
I'll
test?
start up here.
Mm-hmm.
Yeah.
Yeah, just how to calculate escape velocity. You don't have to memorize the numbers. Yeah. Okay, that is it for this. So I'm going to stop recording. Now what I'm going to do is put